We got a lot to talk about. Let's get going. Weather and atmosphere. It's a big unit. I told you that. It's going to take a while. I told you that. Tests might be difficult. I told you that. So we might as well go ahead and get started with this. We are beginning this one at the beginning of the notes packet. I'm going to go off the PowerPoint. I'm going to try something different this time. I don't know if it's going to work. I'm going to go off my iPad. We're going to see. The first thing you got to know is that weather and climate are not the same thing. Weather, short term, right here, right now, outside the window. Climate, long term, 30 plus years. You get the idea. We went over a bunch of different weather factors throughout this whole unit, and hopefully you remember them. I'm not going to list them right here because we're going to hit it as we go. So let's just start with the first thing, which is, of course, the standard atmosphere, or the layers of the atmosphere. There are 4 main layers. Yes, there are more. Yes, I know that there are more. No, we are not going to talk about them right now. We have the troposphere, the stratosphere, the mesosphere, and the thermosphere. In between each of those is a pause. What's a pause? That. But also, it's a change in marked temperature between the different layers of the atmosphere. We note that in the troposphere, where most of the weather occurs, the temperature goes down as we gain altitude. We hit that tropopause, get to the next one, and realize that it's going to start to warm back up. We leave the stratosphere, go to the mesosphere, it cools back down. You get the idea. Most of you, if not all of you, made that graph at the beginning where you showed the different properties of the different layers of the atmosphere, and you noted the changes in the temperature. There you go. So after that, don't worry about memorizing all those numbers. It's not going to be important. After that, we talked about what's in the air and what the composition is. And we probably think that most of it is oxygen since that's what we breathe. But if you remember back to the climate and energy units that we did, we talked about how the atmosphere had to be different back then, and it was up to 30-35% oxygen. That's not what it is now. Most of our air that we breathe is 78% nitrogen. Now, yes, we need the oxygen to actually live, but it's 78% nitrogen, then followed by oxygen, and then a bunch of little things we call trace elements. In those trace elements, we have things we don't think about every day, and we have things that impact our lives greatly every day that we don't probably think about that much either, but we should, like carbon dioxide and methane and ozone. Now, carbon dioxide, not inherently bad. Methane, not inherently bad. We wouldn't have the atmosphere without it, of course. Ozone, not inherently bad and beneficial because it blocks the UV rays coming from the sun in the stratosphere. That's good ozone. Bad ozone is when it's in the troposphere. We call that smog. That's not great. We breathe it in. O3 is the chemical formula for ozone. It messes with the rest of the oxygen. Not a good look. So why should we care about them? We get too much of these things, and it starts to cause that climate change that we're so concerned about. After we move through that, we need to talk about water vapor and water. Now, I know the next unit is hydrosphere, and I know that we're going to talk more about water specifically soon, but without water, obviously we're not here and plants aren't here and there's no life, but without that, we don't get weather patterns. We don't get clouds, we don't get storms, we don't get hurricanes, we don't get tornadoes, we don't get any of this. Water vapor is the fuel for thunderstorms, hurricanes, anything like that. Without it, none of this is going to happen. So, where does weather occur? Well, once again, probably going to be important since I'm saying it so much, in the troposphere, right where we live. That's why it's there. Another reason why, all the water that we just talked about being so important to these storms is located, or mostly located, on Earth's surface. It's much easier to just stay in the troposphere and for it to kind of recycle through there in our hydrologic cycle. So, then, let's start actually getting into those 6 weather factors. The first one is going to be temperature. Now, I don't really need to explain temperature to you. We all understand it. Probably, mostly, especially for you, Fahrenheit. But that's not the only scale. There's Celsius, which is also in degrees. We have degrees Fahrenheit and degrees Celsius. Of course, we know those. But, and maybe you knew this before, most of you probably didn't, or if you did, you forgot about it, Kelvin. Kelvin is not in degrees. It's not something you're going to use in your daily life. It's not something that you're really ever going to see unless you take certain chemistry and physics courses. Now, yes, you might get introduced to it here at the high school in certain different sciences, but once you go to college, if you major in these things or use them a lot in your major, you will need to talk about Kelvin. This is great because it gets to really, really low temperatures. 0 Kelvin is absolute zero. Literally everything down to the tiniest thing stops. We don't need to worry about that. What we do need to know is how to use that reference sheet to look and see what a temperature is in Fahrenheit, then compare it to Kelvin, and then move it over and convert it into Celsius. You need to be able to use that. I'm not going to ask you to memorize any of those factors, but you need to know how to use that sheet. Now, obviously, you use a thermometer to get this, and temperature and heat are not the same thing. We'll talk about that later. Hopefully, maybe if we have time. But we also use it on weather maps, and we use them to check and see, what kind of clothes we should wear today, what it's going to be like outside, is it spring, is it winter, but we have to model it using math. Sorry for those of you that don't like math. And we use isotherms. ISO, same, therm, temperature. So yes, they're ISO lines, the whole thing is an ISO line, but an isotherm is a single line to show a certain temperature. Make a whole map of those, you get to see what's going on across the United States, North Carolina, whatever it is that you want to see. And how does that affect density? Now remember, I told you there's a bunch of different weather factor relationships that you need to keep in mind. I might not say every single one of them in these videos, but that doesn't mean it won't help you to understand them. If you try to just memorize all these things as a fact, not going to go well for you. It'll work, but it's way more work than you should put in. If you memorize how they interact with each other, you'll be much better off because you can reason your way through it. So as temperature increases, as we get temperature going up, we note that density decreases. They're inversely related. As one goes up, the other goes down, or as one goes down, the other goes up. We also know that in the troposphere, as we move upwards in altitude, as we go further up in the sky, we note that temperature goes down. But we just talked about that that's not always true, but in the troposphere, which is mostly what we're concerned about because that's where we live, that's where we fly planes, all that stuff, temperature goes down as we move further upwards. So, how does that relate then to humidity? We all need to worry about humidity, especially in the summer, because we live in North Carolina, it gets really gross outside. Remember, humidity is not the same as relative humidity. Humidity is how much water is in the air. Compare that to the moisture capacity, which is how much water could be in the air. So humidity is water in a glass. Moisture capacity is the glass. What we really are looking at is relative humidity. Relative humidity is the percentage of how much water is in the air compared to how much could be there. How full is the glass, basically, if you want to think of it like that. Now, a couple weird things happen. When the glass is 100% full, when it's fully saturated, we get some kind of precipitation, depending on if it's summer or winter, if it's rain or snow or whatever, but it's going to have some kind of precipitation. We might see dew on the ground. We might see fog start to form. Something is going to happen when no more water can get into those spaces in the air. We also know that since cold temperatures are more dense, they can't allow as much water in between those molecules, which means due to warm air's lower density, more water can get into it. Now this is going to get, again, confusing if you don't keep all these separate. Please start studying if you haven't already. So let's go through, we're going through this. Remember that all of these factors are if you don't change anything else. Now in real life, you can't just change one variable. As I've said before, nothing exists in a vacuum. Everything is related. This is especially true in weather when we can see changes happening because a variable is changed. We can't directly just change relative humidity. Multiple things change. Keep that in mind as you look at these different weather factors. So how do clouds form then? I said clouds, I said fog, I said dew point. Well, you have to hit the dew point temperature. And the dew point temperature is the air temperature needed to fully saturate what's going on. So what does that mean? It's the temperature that the air has to be in order for the amount of water that's in the air to equal the amount of water that can be in the air. So what does that mean? If air temperature and dew point are the same, saturation occurs, clouds are going to form. Again, we're starting to see those connections. Hopefully you're already making those connections if you haven't figured it out already. Keeping these things separate is going to make your life a lot easier when you get to your test. What else do we know? Well, when air temperature and dew point are the same, relative humidity by definition is 100%. We know that some kind of precipitation occurs, and we know that clouds or something like that is going to form. Make sure you know how to use your dew point and relative humidity reference tables. Now, I may or may not ask you to do them on the test, but it's not a bad idea to make sure you know how to use them. Again, it's literally on there. Read it carefully. Don't overthink. You'll be okay. If you still need help, ask me. Okay, we left off last time with me asking you to ask me for help. Now, if you don't need it, great. If you do, awesome. I'll be glad to do it. That's literally why they pay me. We're going to pick up on this one with air pressure. This is weather factor number 3. Air pressure is just the weight of all the gases pushing down on the earth. You can think of it like this. If you're in the weight room and you stack a bunch of those 45-pound plates that you put on the end of a weight bar, stack it up to the ceiling, that's a lot of pressure pushing down on the floor. But if you take away half of them, if we move halfway up in the atmosphere, there's less of those plates above us, which means there's less pushing down on us, which means the further up in the atmosphere we go, the less air pressure there is. And we also know that high and low pressures can be related to temperatures. So what does that mean? Well, cold air is more dense. And since it's more dense, there's more air particles there. There's more air molecules. The more of them that are there, the more it's going to push down, the higher pressure it has. Which means the opposite must be true as well. If it's if it's high temperatures, it's lower density. If it's lower density, there's fewer air molecules there, which means there's less pushing down. It must mean that there's lower air pressure. Because of that, we can think, well, if cold air is more dense means there's less availability for water to get into the air, it must be drier, and that's true. So then the opposite still must be true. If it's warmer, it's less dense, there's more space in between them. More space means water can get into there, which means it's more humid. There's more moisture there. Now again, remember, not all of this is perfectly analogous to going outside. Multiple things change at the same time. This is in a perfect scenario if you could just change a lever or something like that. This isn't how the real world works, but it's a good foundation to figure out how the real world works. We also know that storms are low pressure systems, and we know that the lower the pressure, the worse the storm is probably going to be. Now, is that 100% true all the time? No, not necessarily, but we have a pretty good idea that that's what's going to happen. When we're concerned about it, though, we go and we look at our pressure readings from a barometer. Now, they used to be mercury, then they moved to this thing called an aneroid, which had a bunch of vacuums and springs and stuff. As with everything else, it's all digital at this point. So we get those pressure readings from a digital barometer. 1 atmosphere is equal to 1013.2 millibars, is equal to 29.92 inches of mercury. Do you need to memorize that? Probably it's not a terrible idea. But you also need to, once again, know how to use that reference sheet. You don't always have to memorize things on reference sheets, but you do absolutely need to know how to use them. I'm not going to ask you necessarily to convert anything for a station model, how to go to station model forms, or how to go from the 3-digit code back to the regular. You don't need to worry about that kind of conversion, but you do need to know how to do the reference table conversion. You also need to know how to look at a map and read the different lines. Before we talked about isotherms, now we're talking about isobar. Therm, thermometer, bar, barometer. If you see isobar, that means that it's talking about pressure. It's relating to the barometer, the barometric pressure. Hopefully, if I keep repeating these things, they'll stick with you. Now, you're not going to have to, obviously, on the computer draw it. But once again, reading the map is probably going to be key. All of this temperature, water, pressure differences goes into the next weather factor, which is wind. Wind is from the uneven heating of Earth's surface, which causes differences in pressure because of density. We then can figure out that wind blows from high pressure to low pressure. Basketball can't roll up a hill. It rolls from the top to the bottom. It goes from high pressure to low pressure. Winds will also go from high pressure to low pressure always. Now, that doesn't mean they always go the same direction, but they always go from the area with high pressure to the area with low pressure. It's also important to remember that winds are named that the direction that they come from. You can also think of it like this. Whichever way they're pointing, look at the other end of the arrow, that's the name that it gets. We have some special types of things going on at the coast. If you are confused about it, I'll be glad to explain it. It works exactly the same way, but we give them names called sea breezes or land breeze. What's the big difference here? Look at the specific heat differences between the water and the land. Land heats up quicker during the day, which means it's warmer, which means it has different pressures than the oceans. At night, though, all that heat that's been stored in the water makes it warmer than the land, which flips the pressure systems. The wind is going to move the other direction. All this is in your notes, but keep in mind, you don't have to memorize them. If you can remember specific heat, one is warmer in the day, that makes it have a lower pressure, it always goes from high to low pressure, you get the idea. We measure all of this using a wind vane to determine the direction and an anemometer to determine the wind speed. We can also use gradients and not just the math kind. We can look at the maps, and if the isobars are really close together, there's a high pressure gradient, which means a big change over a small area. We also can determine then that if it's a big change over a small area, the wind's going to blow a lot harder. Hopefully that helps. We'll talk about the next factor in the next video. So with air masses, the thing you have to remember is, one, we've already talked about them in climate, so this shouldn't be new to you. But two, that it takes two different parts. It has temperature and it has a moisture content. The temperature is either warm or cold, tropical or polar. Remember, we're not using Arctic in this one. And the moisture content is either wet or dry. It's wet if it forms over the ocean, it's maritime. It's dry if it forms over land, it's continental. Mix those four things together and you have four different types of combinations. You can get maritime tropical or maritime polar. You can get continental tropical or continental polar. Dry, wet, warm, humid. Mix those around. You have different descriptors for them. Probably not a bad idea to know how to do that. But where do those things come from and why do we care about them in North Carolina? Well, the cold, dry air comes from central Canada and the cold, wet air comes from the northern Atlantic. The warm, wet air comes from the Gulf of Mexico and the warm, dry air comes from Texas. But again, none of those are North Carolina. Why do we care about it? Well, those things will eventually, especially the continental polar from Canada and the maritime tropical from the Gulf, will eventually make our weather as they get here. If they combine in the wrong way, that's how we get our storms and thunderstorms. And if they combine in a really wrong way, that's how we get our tornadoes. But what do we look for to figure this out? Well, fronts. And the front is a boundary between two air masses. And why is it called a front? Well, it's the front. It's the beginning of it. We have warm fronts and cold fronts and occluded fronts and stationary fronts. And what you need to know is that the front is named for the air that's behind it. So a cold front has cold air behind it. A warm front has warm air behind it. There's also precipitation that happens with a cold and warm front. In a cold front, the precipitation occurs at the front. So like where that front line is on a map, that's where it's raining or whatever. A warm front, the precipitation happens before the front gets there. So it's going to rain and rain and rain, and then the warm front gets there. What you should also know is that a cold front has really strong but really quick rain or whatever. A warm front has kind of dragged out, prolonged, gentle showers, or again, whatever, that go along with it. When we get to things like the occluded fronts and the stationary fronts, We may or may not notice differences that happen at ground level, but stuff's going on up in the atmosphere. We might get some turbulence. It might get cloudy. It might get a little rainy. We're not going to notice it a whole lot at the ground level. Whatever we have is kind of what we already have. We're not going to be too concerned about it, but it's good to keep an eye on it from a meteorological sense. That was a good word I just said there. Why do those things matter? Well, you really need to understand all of those things and understand the fronts and understand the different air masses and understand pressure and temperature, and you get the idea. I've said it about a bajillion times. But why? Well, we put all of that together to what you probably thought this was going to be when we started, which is talking about storms and hurricanes and tornadoes and stuff like that. If you don't understand that background, like I've said in every single unit, you're not going to understand the next part. And I'm not going to harp too much on these things because you live in North Carolina. You understand what these storms and tornadoes and hurricanes are. Maybe not a blizzard, but you understand what the rest of them are. Storms are just turbulence up in the air, and there's videos that I've already posted on Canvas which explain some of these things better than I do because that's what they actually study and that's the kind of scientists that they are. But what we need to be concerned about is that water vapor, once again, is the fuel for all of these. That's why hurricanes that linger over the warm water for so long gain strength. They just continue to get that warm water into their system, lower the pressure, and they get stronger and stronger. Weather moves from west to east, and you probably already knew that if you follow the news at all, or if you've seen weather maps before, if you've talked about it in the past. But it also typically tracks northeast. Not always, because again, nothing happens in a vacuum. We have all sorts of different things going on at the same time, but it tracks northeast because the wind is a southwest wind. Again, follow the arrow. It's named for the direction it's not pointing. What should you do to kind of get ready for all these things? Listen to the news, listen to the weather reports, listen to the scientists, all sorts of things like that. If it's going to be a hurricane, we're kind of far inland, so we're okay. Tornadoes, can't really prepare for, but if you hear those watches or warnings, or if you see a thunderstorm watch or warning, or if you see a flash flood watch or warning, just be safe. Think about what safe means. It probably is get to somewhere in your house, centrally located. If it's a hurricane, you need to evacuate if it's possible, or if we think it's going to be bad enough, especially if you're down near the coast. A lot of it's just the same things that we've already said, which is don't be an idiot. Mother Nature doesn't care how strong or cool you think you are. If it's going to mess something up, it's going to mess something up, and it's not going to ask if it's okay with you. We also need to be careful that we don't stand in the path of lightning, where if hail starts to happen, we can seek cover because it can be tiny, can be softball size, can definitely knock you out. I know that sounds extreme and maybe you laughed, the 4 of you that watch this, but it can certainly be a serious event if it starts to hail. It means some kind of crazy stuff is going on in the atmosphere. We should probably be careful. What else do we need to know? Well, you need to know the different scales that hurricanes and tornadoes are measured with. Hurricanes use the Saffir-Simpson scale. It has category 1 to 5. It starts at 75 miles an hour. It has all sorts of different things like the pressure, the surge, the wind speeds, like that. Anything below 75 is either a tropical depression or a tropical storm. The tornadoes are measured by something called the Enhanced Fujita scale. Now, I know that it only says Fujita on here. I forgot to replace it, but it's the same thing basically. They just made a few tweaks. It goes from an F0 to an F5 tornado. Now, something that might be interesting to you is check out those max wind speeds of what a Category 5 hurricane is registered at and what a F5 tornado is registered at. Also, remember that when you see the difference, think about how long a hurricane lasts versus how long a tornado lasts. Which one would you rather be caught in? I don't think there's a good answer to that. Finally, what else do we need to be concerned about with all this? We can't do anything to stop weather. We can't do anything to stop these crazy extreme events from happening. The best we can do is monitor the situation, to understand it, to understand atmospheric science even better than we do as we move forward, to listen to what's going on, and to just be as safe as we possibly can. Now, this was a very quick run through of 180 some slides, and I skipped quite a bit of it, and I did not hit every single thing in these videos. Do not use it as a substitute for class and what we've talked about in class. However, it should help you be able to double check yourself or to figure out where to ask me questions. If you need to ask questions, then please do. Please send me an email, send me a Canvas message, stop me in the hallway if you're walking by, whatever it is you got to do. This test is going to be a big one if you're not ready for it. It might not be a great grade if you don't put the time into studying for it. That being said, if you're taking time to watch this, you're probably going to do great. I hope you do. Thanks.